Okay, in this video I'm going to do logarithmic functions. So the basic logarithmic function um, that I want to talk about is y equal natural log of x, and it's abbreviated with an ln. We could graph functions that have an log of x, which means log base 10 of x. When we're doing uh, ln of x, like I have here, that means the base is really base e. And the reason I'm emphasizing these logarithmic functions is because they are inverses of the y equal e to the x, which we did a minute ago. The exponential function I wanted to focus on was e to the x. These two are inverses. So I'm not going to do log base 10 or log base of anything else. I'm going to do natural log of base, though their graphs would be very similar. Okay, so natural log of x, and this time I only pick the one basic point I want to pick is 1, is actually for x to equal 1. Okay, the natural log of x means like this: net is log base e of 1. Okay, so what it means is the answer to this is actually an exponent. The answer, once the answer I get for my y value answer is actually the exponent I put on the e to this exponent has to equal 1. Well, what exponent would I put on e to make a 1? Okay, anything to make a 1, the only exponent I can really use is 0. Okay, so my answer is 0. So when I substitute in 1, I get an answer of 0. So my natural log function is going to have a point at x equal 1, y equals 0. Okay, and that's really the critical point on this graph. All right, the rest of the graph looks like this. It's like the exponential graphs I did in the last video. You can't really go look at exactly what I have. It's just in general, I'm just going to make it sweep up like it's supposed to. It's supposed to start here toward the y-axis, touch at the point 1, 0, and then sweep up like that. Let me try it again. It looks like it goes down. It always goes up. Okay, as it goes to the right, it's going up very slowly, but it's always going up. So that's pretty much what a natural, in general, that's what a natural log. So again, like I just said, don't look and say, well, that looks like x is 3, and it looks like the y value be 1. That's not the important part. Okay, it is pretty close, but that one point is your critical point, and it goes. That's the shape of the graph. All right. What else you need to know about this graph? Well, this time, the y-axis is an asymptote. I put a wavy line. Asymptotes are really usually indicated by a dashed line. It's just easier to show it with a wavy line. So it's an asymptote. Okay. So that's your basic graph. It's just one you're going to have to memorize. And you can substitute other values for x. You can substitute 2. You can substitute 3. You can a really good one to substitute is actually the value of e, and the natural log when you substitute e is actually equal to 1. So, and if you remember, e is about 2.71 something or other after that. So if you go to write about 2.7, and you go about 1. But you can actually get values if you use your calculator and plug in natural log of 2, natural log of 3. You just can't plug in 0, substitute 0. The calculator is going to say error. You can't substitute -1. You cannot substitute -2 or any negative number at all. So that tells you that our domain has to be greater than 0. And that means it's a positive number. So this is one of the cases where the domain is restricted. Now, the range is not restricted. So Um, we're getting a value down here, um, way down here. That looks like -5. We're getting someplace on the graph that'll give us an answer of -5. We have someplace on the graph that gives us a -3. Of course, we have a point on the graph where we get an answer of 0. Um, pick carefully, we get an answer of 1. And somewhere over here, again, don't take it so literally what x values we're talking about. It's just a general curve. At some x, we're getting a value of 2. So the range is any possible number. So this is the case where the domain is restricted and the range, well, is anything you think of. Alright, so why is that? Okay, actually the log function is the inverse of the e to the x function. Okay, and the e to the x function, I'll do that in blue, had one main point to look at. That was at 0, 1, and it went like this. It went up like this in general. Okay, so how do you know functions are inverses? Well, you draw the line y equal x, which from a linear function it goes right through these diagonal lines. Okay, and these two graphs, this was y equals e to x, which I did in the last video, and this one we're doing y equals natural log of x. Alright, they reflect across that dashed line. They are inverses. Okay, so enough of that. Let's finish the characteristic of natural log. So I'll get this off here. It's important to know why. It's the inverse of e to the x. Okay, what's the interval of increase? It is increasing. Okay, anywhere along this curve, it's going up. Okay, alright, so we can't say all real numbers because the domain is not all real numbers. We say from 0, from to the right of 0 to infinity, it's increasing. It's never going to go down. None. Interval of decrease, none. X-intercept, that key point, which I erased, it goes right here at 1, 0. Okay, that's the point you need to know when you're graphing natural log. X-intercept is 1, and the y-intercept doesn't have a y-intercept. Okay, this is one of those rare functions, and functions will have a y-intercept, except this one has the domain restricted so much that it won't even have a y-intercept. So that's a very rare thing for a function to not have a y-intercept. Okay, the right-hand behavior, it's really the same as the interval of increase as the graph goes to the right, y values increase. Left end, okay, now this one, we're going to say it this way, okay. Boy, the left end is not going toward infinity, so, but it is going toward 0. It is approaching 0, so I'm going to write it this way. As our x values get closer to, not negative infinity, get closer to 0, okay, the y values approaches negative infinity. Okay, so that would be when we typically do left hand, we're talking about going toward negative infinity. I put that down there because it actually will never reach 0, so I kind of think it'll go forever going left towards 0, and so I'm going to say the y values approach negative infinity. So if we put down none, I would definitely understand that, because that graph doesn't go left forever. It doesn't go toward a very large negative number. It goes left forever toward a specific number 0. So I'll leave it at that. let's try another problem. Okay, let's expand on that. Y equals y equals um, natural log. Let's throw an absolute value of x in there, okay? And see how this is different. This is going to be a lot different, okay? First of all, when we picked 1, we got natural log of 1 equals 0. The point would be right here at 1, 0, okay? And any other positive number we plug in, it just look like the last example we did. It would sweep up like this. But the thing about when you put absolute value signs, now we can actually substitute negative numbers. So if I substitute negative number in there, a negative 1, well, the absolute value, change that to a positive 1. Okay, so now natural log of 1 is back to 0. So when I substitute negative 1, because those absolute value signs, I can get an answer. So this time, what I do is I go to negative 1 0. So what the absolute value actually does, it actually reflects this function across the y-axis. Okay, when I plug in a negative 2, I'd get the answer same answer if I plugged in the positive 2. If I plugged in substitute negative 3, I get the same answer if I substitute positive 3. So what the graph will look like is just a reflection like that. That's what that absolute value does. All right, what's the domain then? Because that absolute value feature, okay, now I can use any number, all real numbers, but I just can't use 0. Natural log of 0 is going to be an error. Okay, you can write it like that, or here's an odd way to write it, but it's perfectly correct. From negative infinity to 0, union 0 to positive infinity. That means all numbers except that 0. What's the range? Just like a natural log of x, all real numbers, interval of increase. Okay, because that feature of that absolute value, we got an interval of increasing. Okay, from 0 to infinity. And now because of that absolute value, we actually also have an interval of decrease, which would be negative infinity to 0. X-intercepts, it would actually have 2 because of that fact. At negative 1 we have an x-intercept, and at positive 1. Negative 1 and positive 1. Y-intercept is still will not have none. Okay, the right-hand behavior, as x approaches infinity, y approaches infinity. Alright, since because of that absolute value, we can actually go to the left end, very far to the left. We have a more typical, this would be positive infinity, more typical left end. Okay, next problem, next example. Let's reflect it this time across the x-axis. And let's just use without the absolute value. Okay, negative natural log of x. So the positive natural log of x look like this. Okay, sweeps up. That's probably a little too steep. Like that. So what would the negative natural log of x? It would reflect it across the x-axis. So this section right here would sweep down like this. Alright, and this section right there, instead of sweeping down, would sweep up like that. So your natural log of x, negative natural log of x, would still go to the same point, but it would sweep down like about like this. Okay, domain, anything positive, you have to use a parenthesis there because you cannot use 0. So that means just above 0. Range, um, as it goes to the right, it becomes lower and lower. It reaches any low point you can imagine, and it goes to high um, any high amount you can imagine. All right, is this function increasing or decreasing? Okay, walk toward the right, going downhill. It doesn't have any interval of increase. It's all decreasing from 0 to infinity. X-intercept is still 1. Does not have a y-intercept. Doesn't touch the y-axis because the y-axis just like for positive natural log of x, the y-axis is an asymptote. The right-hand behavior, y approaches negative infinity. Alright, the left end, I'm going to write it just like that problem 2 examples ago. I'm going to let it approach 0. Okay. Go toward the left towards 0. Okay. Y approaches positive infinity. Okay. That's a strange way to write left end behavior. Just to show you what's going on as we go towards 0 from the left, the graph is going up. Alright, next example. Alright, this one we'll try to put both shift left, a shift up or down in both directions. So y equals natural log. I'll use a parenthesis, not a bracket, not an absolute value. X plus 2 minus 3. Okay, the plus 2 is group of the x. That's a shift left of 2. And the subtract 3 means a shift of down 3. So you got 2 shifts that you need to do. And it doesn't matter which one you do first. Just imagine what the natural log graph looks like, the parent function. It looks like this. We're going to shift that 1 point. That's all we need, that 1 point. We're going to shift it left 2 and down 3. So that point would be that blue dot. Okay? So before we try to draw the curve, if you have an asymptote, it's better to draw your asymptote before you draw your curve. On the y equal natural log of x, your asymptote is the y-axis. It's just one line to the left of your point. So to draw your new graph accurately, go one line to the left of your point and draw a wavy line or a dashed line. And that wavy blue line is your asymptote. Okay. Erase your, we don't need that, the natural log of x. We're going to draw the actual answer. So it'll sweep up like this and sort of like that, and just in general. That's all you need to write your characteristics. Domain. Okay, the asymptote's now been shifted to -2. What's the range? Still, every number you can imagine. Interval of increase, it is increasing from -2 to infinity. It's sweeping up. It's never going to sweep down. Does it have an x-intercept? Yes, it will have an x-intercept. Where? Well, it's not really apparent from the graph. We just see it's going to touch. So how we find that out? We're going to use some algebra. We're going to make y equals 0. So we're going to say 0 equals the natural log of x plus 2 minus 3. Well, how do we solve that? We add 3 to both sides. We get 3 is the natural log of x plus 2. And if you haven't learned how to solve logarithmic equation or just don't remember, the way we can get that x plus 2 freed up from that function is apply an inverse function to both sides. So I'm going to apply a base e to both sides. Okay, so on the left I have e to the third. And what happens is the e and the natural log cancel, because they're inverse functions, they cancel each other out. I have the x plus 2. And now I can just subtract 2 from both sides. So it's a funny looking x-intercept, but this is what it would be. E to the third power minus 2. So go up here to my x-intercept, and I could write e to the third subtract 2. And you could actually calculate that and get some decimal approximation. Okay, but I'm going to leave it like that. The y-intercept, okay, and this time it will cross the y-axis. We don't know exactly where. So how do we find that? We make x equals 0. Okay, so we say y equals the natural log of 0 plus 2 minus 3. So that's equal to natural log of 2, subtract 3. And again, you could get a decimal approximation with your calculator. And you could get that way, but I'm going to leave it like that. Alright, the right-hand behavior, okay, I'm going to say the right side is very easy, still easy. As x approaches positive infinity, y approaches 0, positive infinity, excuse me, it's going up forever, sweeping up. So left hand is, to me, it's kind of clunky how I'm writing it, but I'm going to say it like this. And you could just as easily say, well, it doesn't really have a left-hand behavior because it's kind of blocked from going to the left forever by that asymptote. I'm going to say it this way: as x approaches -2, y will approach -infinity. And that's it. That's all I really wanted to show you about logarithmic functions. The basic function y equals natural log of x, and also how to translate it, shift it left or right or up or down, and an absolute value will come into play in calculus. So that's all I wanted to show you. Great job.